All right, and we're back. Let me check to make sure the mic is working. Yeah, it is. Okay, cool. So, orthogonals, orthocenters, what we're trying to find, what we need to do is we need to extend out this side, because if I take this side here and I try to find the orthogonal, right, it's that line right here, I want that line to connect with the opposite vertex. And it doesn't, right? Here it definitely does not. You can see it from the graph paper. It would go down through here. So I need to extend this line out. So extend that line out with me, if you would. Make it dashed so we know it's not a part of our actual triangle. And then you're going to slide it along that extended part until it lines up with that vertex, which you should be able to see if you're doing it on graph paper, right? I don't really need a protractor to find the 90 degree. I can just draw a line. So that is our first orthogonal. It's kind of weird because orthogonals can be outside the triangle. It's kind of weird. I know, it just doesn't look right. What's kind of cool is that if you were to ignore this purple segment right here and focus on these, you'd have a right triangle, wouldn't you? That's kind of cool. So if it's not a right triangle, like it's obtuse right here, we have to extend it out to the right and make it a right triangle to have an orthogonal. That's kind of interesting. If we go to the other sides, right, we want to do an orthogonal from this guy. We'd be sliding along on this, and you can't eyeball that, right? Because that's going to be in an angle. So that's kind of annoying. But we can find it a different way. Let's focus on this part right here. This part right here. If we knew the slope of this line, could we find the perpendicular slope? Yes. Yeah, flip and negate, right? And then we could find where this point right here connects with this line with a perpendicular slope. So here's what we're going to do. We're going to find the slope of this line right here that I'm highlighting in yellow. Okay? How do we find the slope of a line? Rise over run. And what's the formula for the rise over the run? Which goes on top, the x's or the y's? The y's, because it's rise over run. So we have our y's minus our x's. Well, we know these two coordinates. This coordinate down here is over 2, down 3. That was our y. This one is over 5, up 4. That's our x. And this must be our z. So we can take these 2 points, x and y, and find the slope between them. Let's do this in our heads. We're going to subtract the y's. What's 4 minus negative 3? 4 minus negative 3?
7.
7. So that's going to be 7. What's negative 5 minus 2? Negative 7. So our slope, when we simplify it, is going to be negative 1. So that's the slope of this yellow line. What's the slope of the perpendicular going to be? M perpendicular. We flip it and negate it. Well, if we flip it,
it's going to be 1 positive.
It's going to be positive 1, right? 1 over 1. Okay. So whatever our point is, let's say our point was right here. We'd go up 1 over 1, up 1 over 1, up 1 over 1 until we hit the vertex, right? That's what we need. So what we're going to do is we're going to start at the vertex, and we're going to apply our slope until we hit this line, and that's where it's going to be from. Okay? So let's go from here, down 1, back 1, right? That's the same thing as this. Those are equivalent. Everybody cool with that? Right? We can go up 1 over 1, or we can go down 1, back 1. Is that cool? Down 1, back 1, down 1, back 1, down 1, back 1. Where do we hit? Right here. So from here to our vertex must be our orthogonal. So do that on your own and draw in that orthogonal. So there's our other orthogonal. What's cool is that if you focus on this orthogonal, you also get another right triangle, don't you? So does everybody see how I did that? I took the perpendicular slope and I went to my vertex and applied it until I ran into that opposite side. So that must be a 90-degree angle right there. Is everybody cool with that idea?
Yeah.
It's kind of weird. I know it was weird because we had positive slope and then I double negated it. but they're the same slope, right? I could have also gone up 1 over 1, up 1 over 1, and then drawn a line, right? It would have been the same line. So we need to find the orthocenter. Now remember, how many lines do you need to find an intersection? 2, right? So I don't need to find the next one. I could have done it over here if I wanted to. But let's use these 2. Where does the pink line and the red line intersect? Well, right now it doesn't appear to be anywhere. So we need to extend those lines. Extend them out.
It's going to be wherever that
Where they intersect is right here. Does everybody see that? So our orthocenter can also be outside the triangle. It's pretty bizarre. On the outside, yeah. So what's the coordinate of this guy right here? It's 2, 1, 2, 3, 4, 5. 2, 5. That is our orthocenter.
Let me see.
That is our orthocenter. So if you wanted to, now that we know where they intersect, you could find the other orthogonal line. It's going to leave here at 90 degrees, right, and hit this vertex. I'm sorry, not this vertex. It would hit this vertex. Leave here at 90 degrees and hit this vertex. So our next one would be here. That's our next orthogonal. And we'd have to extend this line out to get it. They all intersect there in our orthocenter. Is that okay? Do we understand that the orthocenter can be outside the triangle? You have to extend your orthogonals. What's another word for orthogonal?
Perpendicular.
What did you say?
Height.
Perpendicular, exactly. Perpendicular. Or height or altitude, right? The key is the perpendicular part, right? The 90 degree. That's what we need. Let's try number 7 on your own. Number 7 on your own. Graph those 3 points and see if you can find 2 of the orthogonals and see where they intersect. Do that now. Number 7 on your own. I'll do it as well. I would highly encourage you guys to watch not just my videos, you know, because like my videos are awesome, but also watch the video I posted from Numberphile on Centroids and all the different. I think it's called the Magical Highway of the Triangle or something like that. It's something ridiculous, but she goes through and breaks down the different centers of the triangle really well, I think. So if you're confused of, you know, what does orthogonal mean and what are medians and it's not making sense, watch that video. I would highly encourage that. While you're doing that, I'm going to make a calendar over here. Please do this quietly. Remember, everyone online can hear you, especially now that I've turned the microphone to be omnidirectional. Before I had it just hearing sound from the front. Now it hears the entire room. And I turned up the volume a little bit because people are complaining. So hopefully it's not too loud. So do it quietly unless you want to be on YouTube. You guys all finished with your problem? You're just looking at the calendar in order. That's all we got left there. That's it. I'm working on a final list now. What's up? And see if I maybe today talk about it, see if I can. Fingers crossed, right? Alrighty, so hopefully you did this problem. Did you guys just graph the triangle, or did you actually find the orthocenters? Y'all just graphed the triangle, didn't you? Yeah, yep, I figured. Alright, so let's draw our coordinate plane, and let's do it together. Alright, so that's a really bad axes, set of axes. 0, -1 is right here. This is A. 2, -3, 1, 2, 3 is B. Oh God, is it going to be a tiny triangle? And then 4, 1, 2, 3, 4, -1. Oh God, it is tiny. All right. So there's our little triangle. I'll blow it up that way it's not so tiny. All right, so let me do some hash marks here as well. Okay, so there's our tiny little triangle. What is an orthogonal? Somebody tell me what an orthogonal is. A height. It's a line that goes from a vertex to a 90-degree angle, right? So we need to find what the line is that connects this vertex to this side at a 90-degree angle. Well, it turns out that you can eyeball this, right? Because this is the horizontal side. So at 90 degrees should just be straight up vertical.
C.
And it hits the vertex on the other side nicely. Not only is this a orthogonal, but it's also a perpendicular bisector, isn't it? It cuts this into 2 equal parts. Coincidence. So there's our first orthogonal. How can we find our next orthogonal? What do we need to know about one of these segments? We need to know its slope. How do we find the slope between 2 points? Let's do A and B. How do we find the slope between those two? Euler. Are y'all afraid of being on the internet?
Nah.
Any videos with you guys in them I have is unlisted, so no one can find them unless you give them the link. Alright, so this slope between here and here, we can do using slope formula, or you can eyeball it. Right? It looks like we go down 2 over 2. Right? Right?
It's 1. Yeah.
So down 2 over 2 is -1. So the perpendicular slope is going to be what?
Positive 1.
Positive 1.
Aiden.
So what we're going to do is we're going to go from this point right here, down 1, back 1, down 1, back 1, until we hit this side. Well, it turns out when you go down 1, back 1, down 1, back 1, it hits it right here. Is that okay? That's a 90-degree angle. Where do you think our other orthogonal is going to be? From this vertex to this side, it's going to be here. 90 degree. This is a right triangle, ladies and gentlemen. Right triangles have their orthogonals at the point opposite the hypotenuse. Because that's 90 degrees to that side, that's 90 degrees to that side, and that's 90 degrees to this side. So at what point do we have our orthocenter? 2, -3. Where B is?
2, -3.
Where B is, right? That's where our orthocenter is. The orthogonal from here, it's there. Check it out. If I were to do it with a protractor, I would slide this around on this segment until I got exactly this part right here aligned up with my dot, right? My opposite vertex. And I would slide, still not perfectly lined up, and then boom, there it is. Perfectly lined up, or at least it would be if I'd hold my protractor straight. So there's where that orthogonal is. Same thing for this other side. Slide it, not lined up with the vertex, and then boom, it's lined up with the vertex. So there's our orthogonal, right here. This guy, well, the orthogonal's here. That's where it lines up. So that's the orthocenter. This one has it inside the triangle, right on the vertice opposite the hypotenuse. Let's take a look at this one. Number 8, 9, and 10. It says use the figure for problems 8 and 9. It tells you H, L, I, M, and J, K are what? What does it say? Medians. So J, K, I, M, and HL are all medians. Okay, well, that's cool. Find the area of the triangle. Ooh, that's interesting. So let's first mark up our diagram. If this is a median, what do I know about this side? What do medians do to the sides of the triangle? They cut it in half, right? Medians are basically just bisectors. Not perpendicular bisectors, but bisectors. So we know these are all cut into equal pieces. Everybody cool with that? So the area of the triangle. Well, if we want to know the area, we need to know the height of the triangle, and we need to know the base of the triangle. Well, the height of a triangle would be an orthogonal, right? That's another name for an orthogonal, the height. What are orthogonals? What's an orthogonal?
Perpendicular.
It's a perpendicular. So which of these lines is a perpendicular? Which of these segments, I should say? HL is a perpendicular. So HL is not only a median, but it's also an orthogonal. It's also our height of our triangle. So the height of our triangle is going to be 6 plus whatever this piece is here. Now I told you this is an orthogonal and it's a median. So if this is 6, how much is the little part? How much is that little part then? 3. Because the little part is half the big part for a median. So our height is going to be, the height of the triangle is 9. 9. Okay. So if that's the height, this must be the base. Everybody follow me there? This one must be the base. So I know that it's split in two, but I don't know what either one is. So how can I figure that out? You need to look at the other triangles in there. How can I figure out this base right here? Lucas, what's your thought? So we have a right triangle. The hypotenuse is this part right here. I think what you're trying to say, Lucas, is that this triangle and this triangle are congruent. And you don't know how to say it. But the answer is side, shared side, angle, side. So these two triangles are congruent right here. So that's true. That is true. How can we find out what the hypotenuse is here?
Oh, wait, just add 2 or just times 2.5 by 2.
2.5 times 2 because this is a median. So the little part is half the big part. So this part must be 5. Well, if that part's 5, how can we use that to find this? Anybody? Carson. The really important one, right? The old guy in Greek. Pythagorean. So that's a leg, that's a leg, that's our hypotenuse. So it should be 3 squared plus whatever this is squared, right? Equals 5 squared. Now if you're clever, you'll recognize this is a special right triangle. The 3, 4, 5 triangle. 3 squared is 9. 4 squared is 16. They add up to 25. So 4 is what this length is right here. So if this guy's 4 and this guy's 4, how long is the base? 8. So our base is 8. What's the formula for the area of a triangle? The area of a triangle is base times height divided by 2. What's 9 times 8?
72.
Divided by 2? 36. And it's meters squared because it's area. Now they want to know what HJ is. So here's H, here's J. They want to know the length of this side over here. Well, they tell you this part is 2.5. Don't be confused. That's not 2.5. This is 2.5. So what's the length of this side here? How can we figure that out? Yeah, Carson.
You can use the bottom triangle.
This big triangle?
Yeah, use the big triangle and do diagrams and figure it out.
We don't know that these are right angles, so we can't use Pythagorean theorem, unfortunately. You're thinking here, here, and here, right?
No, I know what he's saying.
What is he saying?
No, I'm saying 6 plus, like,
6 plus 3 is
9.
so 9 squared.
Oh, guys, check this out. This is clever. This is clever. He's talking about this triangle right here. Everybody see it? And he knows this triangle is congruent to the top triangle because this is a 90 degree there. How do we know that's 90?
Because
Linear pair theorem, also CCP, because these triangles are congruent. So their parts are congruent, right? So linear pair theorem, right? So that's a 90-degree triangle. If that's 4, and we know this whole length is 9, we can use Pythagorean theorem to find this guy. Everybody seeing that?
Yeah.
4, 9, this length. So we have 9 squared plus 4 squared equals, we don't know squared, c squared. 9 squared is 81. 4 squared is 16. If we add that up and root it, we get c, right? So 97, root 97, which sounds like a fun place to drive. The root 97. Round answers? No. How about we just have the right answer? Root 97. No rounding necessary. How do you feel about that? That was pretty nice. Nice job, Carson. That was some good. Good eye, good eye, good eye. Alrighty. Remember, Pythagorean theorem only works with right triangles, so we had to show it was a right triangle before we could do it, and we did it with linear pair. Nice. What is the perimeter for number 10? The perimeter of the triangle. We know this whole side length is root 97. We just found it. We know this whole side length is 8. How do we find this side length? Because then we can add them all up.
It's also root 97.
Why is it also root 97?
Because the triangles are
Because this triangle is congruent to this triangle. These sides match up. This shared side matches up. So by CCP, these two sides must match up. What kind of a triangle must this be? A what? Isosceles. So the perimeter is root 97 plus root 97 plus 8. 8 seems like kind of an oddball here, but we'll accept it. So root 97, let's do some algebra here, or really arithmetic. Root 97 plus root 97 plus 8. How many root 97s do I have here? So it's 2 root 97 plus 8. That's as simple as it gets, guys. Perimeter is 2 root 97 plus 8. Were they going to have you round decimals and add them together? Yeah. But why? Why not have the exact answer? Right? Root 97 plus root 97 is 2 root 97. If I told you, 3 plus 3, we could write that as 2 times 3, right? That's 2 3s. So why not just write it as 2 root 97s? That's what I'm talking about. Nice job, guys. Nice job.
right.
So 2 root 97s plus 8. Number 11, I'll let you think about. Not necessary to do, but I'll let you think about it. Let's talk about 8-4. This is kind of, I don't think it's too complicated. We're going to throw this in here at the end and try and squeeze it in. 8-4 is about the mid-segments of a triangle. And I mentioned this, I think, a little bit in the other class. I always get you goofed up with my single block. I don't think I did. Okay? It is, I'm sorry, I always call them single and you double. You are single. I always get you goofed up with my double block. Mid-segments sound a lot like medians, right? Do not confuse them. They're similar. If I draw a triangle, how do I find the medians? Let's talk about what we do know. The medians. How do I find the medians of a triangle? You're thinking of the orthogonals. You're thinking of orthogonals.
Oh.
What are the medians?
Just a bisector to the inverse.
Nice. So the midpoint to a vertex. The midpoint to a vertex. The midpoint to a vertex. Those are the medians. And their center is the what? Medicenter, also known as the centroid. And what is the function of the centroid? It serves as the what of the triangle? The balance point. And then what does it cut the medians up into? 2/3, 1/3. Yeah, a 2-to-1 ratio, 2/3, 1/3. That's what I'm talking about. All right. So, whoa. If you're wondering, yes, I did just smack a child. I had to. It's just part of my teaching. All right, so here we go. Sit down, Lucas. Sit down. All right. Let's grab another triangle. Here's another triangle. The mid-segments are different than the medians. Let's use a different color. Let's use blue. Here's what the mid-segments are. The medians were a midpoint connected to a vertex. The mid-segments are going to be the midpoints connected to midpoints.
Ooh, I was right.
Oh yeah, Triforce. All right, so the mid-segments are the segments that are made when you connect midpoints. Triforce. 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 All right, so what's cool about this? Here's what's cool about mid-segments. Two things. One, check out this side. Check out its mid-segment that's opposite it, this guy here. They are parallel. And not only are they parallel, but they are also in ratio to one another. Turns out that this guy right here is half the length of this side. So if I call this side x, how much is this? Half x. Pretty cool. That's what it's about. Are we okay?
Yeah.
All right, we're fine. No Snapchat. All right, so like and subscribe, please. Otherwise, I'll have to take down another child. Sorry, Lucas. If we don't get enough subscribers, I'm going to have to hurt Lucas. It's just part of it. All right, so the mid-segments. Pop quiz. The mid-segments are the segments formed when you connect what?
The midsection.
The mid-points. Very good. What is a median? Somebody explain a median to me. I need a hand. Someone other than Marcus. He's on fire today. He needs to cool down a little bit.
I do it.
He needed to be cooled down. Who can tell me what a median is? Joey. Midpoint connected to a vertice. Pop quiz. Nobody answer. We're going to answer all at once in a couple seconds. Midpoint.
Yep.
What is that? What's the blue? What is the blue? It's a what? A median. Yeah, I did, but you're enough, Natalie. You're enough. What about this one? Midpoint. What's that? What's the red? What's the red, everybody? Mid-segment.
My bad.
What do we know about the mid-segment? Midpoint to a midpoint. What else do we know? What properties does it have? Marcus.
It is 1/2 of its.
So if that's x, this is half x. And what else do we know? One last thing. They're parallel. They are parallel. So the angle here is the same as the angle right here. That's pretty dope. Yeah. Right? And the angle here should be congruent to the angle here. Because they're parallel. Alrighty. So that's the difference between midpoints and mid-segments. Let's use that information to solve these problems. So let's take a look at number 1. It says find HI, the length of HI. Let's zoom in on this triangle and find HI. Well, HI is here, my dudes. That's HI. That is HI. If we knew that was a mid-segment, it should be half of this, right? Is there any way to prove that this is a mid-segment right here? Remember, mid-segments are parallel, and they're also half the length. We don't know the length. How do we know it's parallel? Because they look like they are. So, I'm going to regret saying this on YouTube, where it's permanent and people can make fun of me if I'm wrong. But I don't think we can prove that that's a mid-segment. I don't think we know. Right? If that's 58 and that's 58, then yeah, they're parallel, right? Because they're both going off at the same angle. Actually, that's not true. If whatever this is the same angle as... No, I'm sorry. Whatever this is the same angle as this angle. If those angles are equal, then yeah. But how do I know that? I don't. I don't know that. I don't. And I don't know that this is half of that. So we are going to assume. Let's do this. Let HI be a mid-segment. I think they didn't give you enough information for this problem. And I'm going to regret this, I'm sure. Someone's going to point this out that I'm a complete idiot and there's something obvious here and that I'm missing. And they're going to leave it in the comments, which you should, right? Like and subscribe. from what I see, I don't think there's enough information. So if that's a mid-segment, how long is it?
Half of ED.
Half of ED, which is
9.1.
9.1. Very good, very good. Number 2 says find DF. Well, I found it. Here it is. What's the length of DF is what they want to know. How can I find that length?
17.5 is parallel to ID.
We need to also say that G is a midpoint. So if G is a midpoint, this and this are equal. What does that make HG? If G is a midpoint, what does that make HG? A mid-segment. So how much is FD?
Double.
35.
I said
Nice job, Natalie. Thank you, Marcus. Is everybody cool with that?
Yeah.
Amelia, put the phone away, please. Can't believe I have to say that live on YouTube. How embarrassing. Wonder if your parents like and subscribe. Amelia's normally awesome. This is just a weird day for her. I think it's Scudet's fault. All right, so 5 DF is 35. And I can say your last name on... yeah, that works because it's not really your last name. I just made it up. That's perfect. Good thing I don't call you by your real last name. GE. How do we find the length of GE? I bet you can figure it out on your own. Moving on. How about HIF? HIF. That's this angle right here. HIF. How do we know that angle?
Oh, me.
Marcus.
We know that it's 58 degrees
Why do we know it's 58?
because alternate interior angles.
That's what I'm talking about. All right, guys, check it out, check it out. We know because this is a mid-segment, it is parallel to the opposite side, right? These are parallel. So what is this? A transversal. Bam, 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 bam. Guys, check it out. You remember this?
Yep.
You remember this, right? You have a line cutting 2 parallel lines. So alternate interior angles, it's 58. Nice job, Marcus. What about HGD? HGD, this angle right here. How can we find that angle? This angle right here. It's what Marcus did last time, plus an extra step. I'll give you some time to think about it. This is a mid-segment, right? This is a mid-segment. We know this segment is parallel to this guy, right? So what must this line be? We have 2 parallel lines cut by this guy. That's a, starts with a T, transversal. So if that's 58, what measure must this be?
58.
And if that's 58, how much must this be? $122 by linear pair theorem. So that's this guy, 122. The rest is on your own. Enjoy the Bermuda Triangle problem. I feel like that's a good one. It's a lot of big numbers and it's ridiculous.
It's really easy though.
Best of luck on these, ladies and gentlemen. And we'll be signing off now. That was Mr. Mack, third hour, 3A. We've been doing geometry today, 8-4 and 8-3, mid-segments. We've talked about altitudes. We've also talked about
Bananas.
medians, not bananas, but now we have. Like and subscribe, and leave a comment of bananas so I know that you made it to the end of the video. Enjoy.
My name is Davis.